Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 70. So in today's lesson, we're going to we've been, in the last few lessons, we've been looking at trees and before that, data structures in general. We're going to hold off on picking up that again for the next lesson. And I think we'll be moving on to another type of tree called red-black trees. Today we're just going to do a little bit of just basically a recap of some of the binary, so how the computer works. So we've at least touched on this, but maybe not looked into it more that in depth. So we'll just look a little bit in depth today. Consider this like a little side lesson. We're back in VS Code. Could have done this in Writer or Visual Studio, but I feel like Code's going to be fine for this, so we'll just use it. So what we're going to try to look at today is how computers store integers, or how they handle negative numbers, some of the binary operations. So there's ways you can work with binary numbers itself. Maybe even look a little bit at overflowing and how C# handles overflows. So a lot of topics, but I think we'll go pretty quick. So we'll hop right in. So I have a text file here so we can do some numbers. So first thing, let's just look at some binary and let's make sure we understand them. So my computer is a 64-bit computer. So that means numbers in it, for the most part, it treats them as 64 bits, and that's a lot. That's basically 64 ones and zeros. So something like that. That is a pain to work with. So that would be hard to look through, hard to show anything with. So we are going to consider ourselves 8 bits. 8 bits. 1, 2, 6, 7, 8. Something like that. So first thing, let's do a decimal to binary. So 1. We'll add some space here just to, let's add a tab. 0, 0, 0, 0, 0, 1. There we go. So binary is a way of expressing numbers. So their normal way is called decimal. So decimal are base 10. So binary is base 2. Something like that. So the normal way we do it's in decimal, but computers represent things in binary, and the reason for that is a lot of the logic in a computer is really just a switch. Is this switch powered on or powered off? Is it a 0 or a 1? And that's our abstraction and what a lot of the computer is actually based on. So all the numbers really are patterns. So here is an 8-bit version of this. So the first bit stands for 2 or 2's place or 1's place, and then the next one's a 2's and so forth. So that might seem strange at first, but if we extend our example here, you can have multiple ones checked at the same time. I can type there. We can even do ones like this. There. So 10. So we can do multiple numbers. In fact, for 8 bits, the largest number we can do is 255. So how do we get those numbers? So each bit represents a position of value. So this is the bit 0. This one is a 1 or 1's place, 2's place, 4, 8, 16, 32, 64, and 128. This sort of adds up. So here what we could say is This one's not, well, this one's not interesting, but if we added some more things here, we could do summed up values. So here we could say for each place here, it's basically this 128 times 0 plus 64 times 0 plus 32 times 0 plus 16 times 0 plus 8 times 0 plus 4 times 0 plus 2 times 0 plus 1 times 1. That equals 0 plus 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 1. That equals 1. So this one's going to be very similar. We'll just copy out this actually. And we'll make this one a 0 and this one a 1. And then we get here 2 and 0. And what do you know? 2 plus a bunch of zeros equals 0. So a 10, it's a little more interesting. So 10 has the 8's place also checked and the 2. So 8. So this one. So this one becomes 8 plus 2, which is 10. And for the last one here, oops, everything's checked. So then we get 128 64 times 32 times 16 times 8 times 4 times 1. So that equals 182 plus 32, so 204 plus 16, so 220 plus 8, 228, 232. Well, I've done the numbers wrong. Hold up. We'll do a calculator since I apparently can't add in my head anymore. Plus 64 plus 32. There, I messed up that quickly. Plus 16 plus 8 plus 4 plus 2 plus 1. We get 255. I don't know where my numbers were going. $255. So that's sort of what's happening. So does that make sense? So the way we interpret a number like 255 is actually the same way. So if we have 255, what that says is you have 5 ones. So 5 times 1, 5 times 10, and 2 times 10 times 10. So what's happening there, we could say instead, this is 10 to the first power, or 10 to the 0th power, 10 to the first power, 10 to the second power. If you add all those up, what you will find is you get 255, and that's really what's happening here. Each one of these is 2 to some power. So if we get that fancy calculator we had here again, if we raise 2 to the 8th power, this one, 2 to the 8th, we get 256. But we only got 255 here, so what's happening? So in computers, the 0 also counts. So if you add a 0, so we can hold up a number up to 255, but you also have to count the 0. So that's where that's why the number there's a slight discrepancy. It's always this number minus 1. So if you have 32 bits, you get a much bigger number. 2 raised to the 32nd. It's going to be something over 4 billion, 4.3 billion basically. If you do 2 to the 64th power, that's what if you have a 64-bit computer, which most modern computers are, you have that many bits to play with. And I don't even know, let's see. Million, billion, trillion, quadrillion, quintillion. So 18 and a half quintillion. So either way, really large numbers. And that's how computers store numbers. So that just seems to work out. Caveat. How do you, if this is one, if it goes from 0 to 255, what do you do about -1? So this works fine for a byte or an unsigned int. It doesn't work fine for a signed byte or an int. So the signed integers do something a little differently. So they do something called 2's complement. So complement's just the opposite. So to do 2's complement, you write out the number is positive. So if we grab the 5 up here, let's do 5. So 5 equals that in binary. So -5. How did I get in override mode? So -5 equals, we do a little bit of work. So we start out with that. Now we flip all the bits. So any bit that's set, or anything bit that's a 0 becomes a 1, and any one that's a 1 becomes a 0. So 1, 2, 3, 4, 5, 0, 1, 0. Then we do one more thing, +1. And that gets us 1, 1, 1, 1, 1, 0, 1, 1. And that, close the calculator. That, if we pull up our nice shiny calculator, go to programming mode, and go to decimal, and then we type -5. That's a great big number, relatively speaking, but if you look, the third number is 0. If you look at this, I bet there's I bet that's 64. 6, 7, 16. So yeah, 64 bits there. I wonder if you can set that. Yeah, there we go. Hot. So yeah, so there. And that looks very similar to what we have here. So that's called 2's complement. So to get the negative number, you start with the binary or the regular number, you invert it, you take the complement, and then you add 1. And that works for everything. So when you see ranges for signed values, let's do this. Let's go over here. Let's do this. Let's do sbyte.max value console.writeLine sbyte.max value s plus, I could not type, plus sbyte.min value. And let's see what that does. And for good measure, let's do sbyte. And we'll do a regular byte here, just for good measure. Let's see what happens. So let's see, .NET run. I think that should be good since we have a CS proj here. There we go. So the range for a byte is 255 to 0, which matches what we did. The range for sbyte is not that. So what happened there? So the first byte goes away. So the first byte's used to represent if it's a negative number. So if the first byte's a 1, it's negative. If it's a 0, it's positive. That has an implication, though. That means there's only 7 bytes we can deal with. So if we add these numbers up here, let me grab my calculator one more time. So if we add up those numbers there, so 64 plus 32, 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, we get 127. That's still odd. The negative number is 1 less. So here we had to count for 0. So that one made sense. Why is this one a bigger? It's a smaller number, but it's 128 versus 127. What's happening? So 0 has to be accounted for somewhere. Just like we did here, you had to account for 0 somewhere. And the convention is 0 goes on the positive side. We know from math 0 is neither positive nor negative, but if you look at a signed number that's all zeros, that was more than 8, that is 0. If you look at one that's all that is -1. And if you do, here, let's pull this up and make it easier to see. If you do -1, it is all ones, -1. There, the first bit changed. Third bit. So it seems to be going sort of like you would expect for numbers, but there's something strange going on. So there, 5. It's like everything's shifted just a little bit, and that's because it's starting negative. So that's why the range here is like this, though. So you can think of it as zeros on that side if you wanted, or you could also think of it as the value -1's the biggest number, and everything else is getting smaller until you get to 0. And then this one flips, and then it keeps getting smaller. So -1's the largest number, and then all the way down to this number, the number keeps getting smaller until it gets to 0, and then everything until it gets to that number, then it goes to all the way to everything's 1 except the first bit. So we'll see why that is here in a moment. So I guess the other way to say it, there's one more negative number than positive number. So why does 2's complement exist? So you had to have some way to keep track of the negative number. So 2's complement's nice because you can do this. So let's add some binary numbers here. So let's add a 5. So we'll just grab these. We'll grab this. Then we'll grab this. Sorry. Grab this. Now if we add them together, what do we get? So binary, we just add values as you would think. You have to start at the side. So let's do this. So these two add together, and we carry the 1. So this one, you now have 2 1s. 2 1s equals a 0, and we carry the 1. 2 1s is a 0, we carry the 1. 2 1s is a 0, we carry the 1. 2 1s, 2 1s, 2 1s. So we get a 0, and then there's an overflow of 1. So what do we do with the overflow? We just discard it. For a 2's complement like that, we don't actually need to worry about the 1. So that gives us a result. So 5 plus -5 equals 0, and there is an overflow, but we don't care about the overflow. And that's the reason for that, is it makes addition easy. So addition still works normally, so there's no need for special. So everything in the CPU has to have hardware associated with it. There has to be some wires and machinery to do any kind of math. So that doesn't require anything different. It's just the same addition. It just so happens to work out just fine. And that's where 2's complement actually comes from. So there's a little bit about the background. So let's do a little programming example now beyond what we already done. So let's just put together a real quick program here. So let's mess around with binary numbers a little bit. So int a equals 5, int b equals -5. Not being able to type, this might be bad. So we'll do print binary a, print binary b. There's no print binary method though, so let's add that. Static void print binary int value. So this should look pretty similar. Everything should be fine. So now we'll do a convert.toString value 2. So the convert here takes a value, so that's the value we're passing in, and then to base is what we're converting to. The base of the result, which must be 2, 8, 10, or 16. So those are important ones in computer science. 2 is binary, 8 is octal, 10 is decimal, and 16 is hexadecimal. If we look here, that's the values you have on the Microsoft calculator as well. So we'll need to do a little bit. So we'll do pad left 32, 0. So 32. Let's just do 8. Let's see if it'll do 8. Let's see what happens. So now we'll do console.write value equals binary. There. So now if we write that out, let's see what happens. Eight looked fine. -5 didn't. So what happened? So it was able to do it was able to handle 5 just fine because everything above this point was zeros. So it says, okay, we'll just take the zeros. If we don't pad left here, like if we just do this, what we'll see is that it'll just be 1, 0, 1. The other one's still long, so what's happening there? So that's where what I was originally typing came out. So originally I was going to do 32. So the reason for that is that int is int 32, and int is the size. So that's the number of bits it takes. So the negative there is also -5. And we'll notice this will compile, even though int 32 is not int, it actually is int. So that's what's happening there. So there's a bunch of zeros that at 8 are being cut off that at here you can actually see. So that's basically what's happening though, and you'll see that that looks very similar to our text example. A whole bunch of ones and then a 0 in the third position. And we'll see if you play around with negative numbers, you'll notice that it just so happens to work out like that. So if we add them two together, what you'll see, we'll do print binary a plus b. You should see a 0 here on the last one. And you do. So good. Math worked out. So now let's look at a little bit more on bits. So beyond binary, or besides being able to print binary and do the conversions, you can also work with bits directly. So let's add some values here. We'll do int x equals 12, int y equals 10. So console.write line. So x and y equals x and y. So notice I'm only using one and. That's it. There. there's something to that. We don't need them, but we'll leave that. So X or Y. Again, notice I'm using one or. Now we're going to do one I don't think I've showed before. X caret Y. So what the caret stands for is XOR. And we'll see what that does here in just a second. So we'll add a new line here. So let's see what happens. And we'll explain these as we go. So 12 and 10 equals 8. Does it? 12 or 10 equals 14, and 12x or 10 equals 6. So let's see what happened. So let's get our binary here. So 12 in binary equals 2, 3, 4, 1, 1, 0, 0. Like that. 10 equals 0, 0, 0, 0, 1, 0, 1, 0. All right, so let's see what happens. So 12 and 10 equals this and this. And I probably find it easier to do it horizontally, actually. Or vertically, sorry. Not horizontally. So the result here, we get anywhere that the two of them match. So here they're both 0, so it's a 0, 0, 0, 0, 1. Here they don't match, so it's a 0, and a 0. I guess anytime they're both 1, the AND works out. And this is the 1's place, 2's place, 4's place, 8's place, so 1, 8. And we got an 8. So that worked out. So if we do that again, but we do it with an OR, what happens? So in this case, we're saying anywhere that it's either the top one or the bottom one is a 1, output a 0. So zeros, 1, 1, 1, 0. So what do we think that is? So 2, 4, so 6 plus 8. 8 plus 6 is 14. So we got 14. So that worked out. What about this last case? What was this? So I said it was called XOR. So here, what you set is anywhere they're different. So if they're both the same, so both zeros, you get a 0. Both 1s, you get a 0. Here, where they're different, you get a 1. Here, where they're different, you get a 1. You get a 0. And that equals 4 and 2, which is 6. So those are the XOR and an OR. So and, once again, and is true if both bits are 1. So both of them, so both bits there have to be 1, then you get a 1. So and is useful. It's something called masking. There's other uses as well, but they're just doing that. Like say here, we needed to see what values these two are. Or we wanted to hide the values. So what you could do is what am I wanting to say? I'm trying to think how I want to phrase masking. Basically here, this one comes through, but everything else, anywhere that, no matter what the rest of these values are, since it was a 0, everything else was hidden basically. The next one was ORs. So this one, it's pretty straightforward. Anywhere that one of the bits is a 1, it becomes a 1. And OR is useful for combining flags. So I think we've actually looked at flag variables maybe once in the past, or flag enums. But basically, you're doing that and you're saying if any of these positions, this one or this one are set. Third one, XOR. So interesting for it is it can toggle things. So notice these two swap places. So that them two, the values that were the same got swapped, the ones that weren't didn't. One other interesting thing you can do with an XOR. Let's do this. What do we think if you do 2x's here? What do we think that becomes? And it's a 0. So what's happening there? What did I do? 2 12. So we'll grab 12 here. So there it becomes 0 because they match. So I actually don't know that it was actually more efficient, but a lot of times if you're ever looking in low-level programming, so assembly, what language that a lot of stuff goes down to, a lot of times if you have something that's a 0, that's what it'll do is you'll see to make something 0, you just add or XOR them together. And I don't know if that actually is more efficient or anything, but you will see that occasionally. All right, let's do. Let's look at another one. Let's look at another one. Let's do yes. We'll do let's add those two. So that is a bitwise not. So the interesting thing there is it flipped all the bits. And that gave us -6. So let's see why that is. Let's grab the 5 up here. Let's see which one's it. These two. Grab these two. All right. So applying a not, we get 1 1 1 1 1 0 1 0. All right, wait a minute. Yeah, not. We flip all the bits. So that, and my intuition for that is not great. But if we come over here and type that in here, we get -6. Yeah, -6. If we do that here, however, it goes, this one's a little easier to see. So here it becomes 0 0 0 0 0 1 0 0, which is 4. So those matched up. So that's just flipping the bits. So you can occasionally run into that. So another interesting one that you can do with bits is called shifts. So there's a left shift and a right shift. So let's do this. We'll put these separately. So we'll do console.write line. We'll just do a 1. Let's do int value equals 1. We'll do it like that. So value shift here. Shift 2, shift 3. So what do we think is going to happen there? And let's do it like this as well. Let's do print binary value. Why does it keep doing that? Value shift 1. And I hope I've got the shift correction right. Otherwise, we're about to be very disappointed and have to flip them. Yeah, okay. So we get 2, 4, and 8. So looks like that's just multiplying. So what's happening? So that's quite literally, it shifts the bit to the left. So we have 1, shift the bit 1 position to the left, you get 2. It's over 1 position. Shift it 2 bits to the left, you get 4. 3 bits, 8, and you could keep doing that with more if you want. You could also go the other direction. So I don't think from this we're going to get anything interesting here, but we'll just do this here just to see what it is, but this one won't be interesting, I don't believe. We'll add a CW right here just to end the line. Let's switch all of these from here on out. Control V, Control D. We'll switch them the other way. Well, we would have switched them the other way. There. So this one, I don't think you're going to see interesting. You're going to notice they all become 0. Yeah, all become 0. So what happened? So it shifted it off this direction to the right, and it went away. So let's do something a little more interesting. Let's set value equal to... we'll do 16. Now, let's see what happens. So now, we have the 1 and the 16 bits. We shift right, we get 8, 4, and 2. So it's basically just going up and down shifting, and you're like, what's the use of that? And I'll be honest, I haven't used it directly myself. But where I think you could see shifting is with if you had to do a lot of multiplication and division. With computers, division is really slow, so a lot of times it'll actually be doing shifting instead. Multiplication can be slow, but I think it's actually sped up most of the time. I think division's the slow one now. So if you look underneath at what the compiler is actually doing with your code, if you're doing a division, you might be doing some shifts just from that. So what it's basically is left shift you're multiplying by 2, right shift you're dividing by 2. And you can use that to play around with addition and multiplication sometimes. All right. Let's do just a little more. So now let's do byte value equals 255. So max size. We can use value again. Let's do we'll just do V. So V plus plus CW V. What do we think happens there? So 255, and we add 1, we get 0. It overflowed, and that's not that hard. So we add 1, 2, 3, 4, 1, 2, 3, 4, and we added 1. So then we do all the carries, and we get 1, 1, 2, 3, 4, 1, 2, 3, 4. The overflow. And once again, we've discarded the overflow, so we're left with 0. So that's overflowing, and you can get some bugs occasionally with that. Always something to keep in mind. So C# has a way to deal with this, though. So let's do this. So if you notice, this one didn't throw an exception or anything. It just let me do this. So this copy that. I wanted that on the next line, but So this is the equivalent to something like this. So a new keyword we haven't seen in C# before. Unchecked. So if we do unchecked here, what we will see is both of these become zeros. By there being unchecked, though, that makes you think that there's also going to be a checked. So let's see what it does. We'll grab the whole thing. It won't matter, but we'll grab the whole thing. So let's see what checked does. If we run, unhandled exception, system overflow. Arithmetic operation resulted in an overflow. So checked. So unchecked says, okay, just overflow, be fine with it. Checked says, okay, this overflowed, throw this exception. So sometimes you'll need one or the other, and I actually have used checked before to make sure we didn't overflow. But it's rare, and a lot of the times you'll just leave it as the default, which is unchecked. Let's see, anything else we'd like to discuss? No, I believe we're going to stop there, actually. So where might you run into this? If you're doing low-level coding, you might possibly run into this. If you're running maybe some maybe networking, so messing around with bits coming across the networks, you might run into some bit operations. If you're doing any kind of like file permissions, file system permissions, cryptography, you'll see a lot of that with cryptography a lot of times. Maybe if you're doing some kind of really optimized programming, like maybe you have a special CPU. One of the ones I've worked at work doesn't actually have division, so you have to do something else. And it's actually got it built in a way to do it, but it's really slow, so you have to do something else besides division. But that's sort of just a covering of what we wanted to go over. So let's see, anything else in my notes? So a negative number is not stored separately. That you don't get any special storage for a negative number. It's just a 2's complement. And the reason you do that is so that the CPU can have the same addition circuitry. So you can have positive and negative. I think that's all I wanted to cover. I mentioned we could look into the flag enums, but I'm not going to do that. We're actually closing in on time, and I didn't prepare anything for it, so we'll just say this is good enough, and we'll call it here. So next time, I'll be away on a vacation, so it'll be recorded in a few days, but this one's recorded ahead of time. So next time we'll be looking back at trees again, and we'll be looking at the red-black tree. So we'll call it there. So thanks for watching, and have a wonderful rest of your day.